everybody, this video is going to be about gas stoichiometry. Gas stoichiometry is what we get when we combine the gas law chapter and the stoichiometry chapter. Remember I said stoichiometry was not going away? Here's a perfect example. So in stoichiometry you use conversion factors to get from one unit to the other. This time you're still going to use stoichiometry, you're still going to use conversion factors, but once in a while you may have to use gas law equations to get some of the values that you need. So we're basically squishing these two ideas together. So we're just going to go through a couple problems. There's not really anything to lecture you on. It's really just showing you how some of these problems are set up. So remember, in normal stoichiometry, you're just using things like molecules, masses, molar masses. Maybe you're using some metric conversions here and there. But for the most part, it's things like Avogadro's number, molar masses. So we're still going to do that here. You're still going to need things like mole ratios, right? Because we're still going to be having equations that we're dealing with. But you may need to be using your gas laws to help you find some of your numbers. So for example, this should look very familiar. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. You would normally use molar mass of A, use mole ratio, use molar mass of B. That should just seem like old news to you. But here's where the new part's going to come in. You may not be given grams. You may not be given moles. You may instead be given pressure, volume, and temperature information about A. And you may be given pressure, volume, and temperature information about B. And so the problem here is, well, how do you get from these to moles? Well, we have a perfect equation for that, don't we? We have ideal gas law. So in these conversions here, instead of using molar mass, you're going to use the ideal gas law and solve for moles. And then that will allow you to get where you need to go in your pathway. Once in a while, you may be able to use things like molar volume, which is a memorized answer to a question, okay? So 22.4 liters per mole is what you get if you are at what we call STP, standard temperature and pressure. If you're at standard temperature and pressure, and you use the ideal gas law, and you put in that you have 1 atmosphere, and you have 0 kelvins, and you have 1 mole, the volume that you get when you solve that ideal gas law is 22.4 liters for your volume. So you're basically memorizing an answer for a specific temperature and pressure to save you this step. You can use it as a conversion factor instead of having to actually do the ideal gas calculation. There's other shortcuts that people sometimes memorize, like SATP. That's called standard ambient temperature and pressure. So there's a variety of these memorized answers. Honestly, what I've noticed is that people will use those incorrectly. They'll use them at the wrong times. So it might just be safer to use the ideal gas law each time. That will always get you the right answer, right? But it is a little shortcut if it works. So here's sample problem 1. CH4 burns an oxygen gas producing CO2 and H2O. A 1.22 liter CH4 cylinder at 15 degrees Celsius has a pressure of 328. So you can see we have some kind of a chemical reaction happening, so it's going to probably involve stoichiometry. And we have pressures, temperatures, volumes, so it's going to involve gas laws. So the question we get is, what volume of oxygen at 100 kilopascals and 298 Kelvin will be required to react completely with all of the CH4? So first let's balance our equation. And now let's write a pathway. So I don't know how many grams of CH4 I start with. I don't know how many moles I start with, but I do know how many liters. So I can go from liters of A to moles of A, moles of A to moles of B, moles of B to liters of B. I cannot use molar volume 22.4. I am not at standard conditions, right? So I'm going to have to use ideal gas law instead. That will help me find moles. Once I have moles, I can use a mole ratio conversion factor. And then they want to know, once you're finished, you're at different pressure and you're at different temperature. So what we have to do is we have to plug it back into ideal gas law to figure out what the new conditions would be, okay? So we are starting with liters of A, ideal gas law to find moles of A, mole ratio, conversion factor, dimensional analysis to get moles of B, plug it back in to ideal gas law with the new temperatures and pressures, and find out how much the B gas would take up space. Okay, so let's give it a try. First step is liters of A to moles of A. Using ideal gas law, our starting pressure, volume, and temperature, remember, convert your temperatures into Kelvin. Go ahead and pause the video and you try to plug everything in and you try to solve for moles. All right, so some people prefer to rearrange the equation first. I personally am not that person, but I'll do that for this lesson to just kind of show you that the units will cancel, because sometimes people get stuck about that. So it'll be a little bit easier. So I'm going to do PV divided by RT, and that will get me moles. So pressure, volume, divided by the R value, and divided by temperature. Because I'm in kilopascals, I need to use 8.31 as my R value. Now if you look, we have kilopascals and those cancel. We have liters and those cancel. This is on the bottom of the denominator here, and this one's on the top of the denominator. So those will cancel. So when you're all done, the units you get are moles. So we get, if you burn that many moles, right, that's the same as if you had 1.22 liters at those conditions. We're not done. Now we have to get to moles of B. So now we're trying to get from moles of CH4 to moles of oxygen. So I'm going to use mole ratio this time. This feels nice and simple, going back to old stuff. There's 2 moles of oxygen for every 1 mole of CH4. Those cancel nicely, and I get my moles. I'm not done yet. Now I have to see how much space would that number of moles take up in the new temperatures and volume, or new temperatures and pressures. So now we're back to an ideal gas law question. I have new values. I'm going to use ideal gas law. You plug it in and you solve for volume. Go ahead and pause the video and give it a try. So moles, R value, temperature, pressure, all punches out in my calculator to tell me I'm going to end up with 8.28 liters of oxygen gas when that reaction has finished and we're at those new temperatures. Okay. Now I'm going to add a second question. Same problem, but now I want to know how many grams of water are produced. Well, I already found my moles of CH4, didn't I? So I'm just going to use mole ratio to get to water, and then I'll just use molar mass to get to grams. So one of the things that sometimes confuses people on these gas stoichiometry problems is that not every single problem or every single part of a problem will involve a gas law equation. It just means that somewhere in the process you had to use gas information. So don't panic if you get a problem that looks like regular old dimensional analysis from start to finish, okay? Sometimes, part A you use gas laws and part B you don't. Or part A you don't and part B you do. So it just means somewhere in there will be gas calculations. So my moles of CH4, 2 moles of water for 1 mole of CH4, molar masses, and I find out 6.02 grams of water will be formed. Now let's do another part. All right. So now, new problem, but we're going to just be using the same equation. Okay, so it's just kind of a continuation. We want to know what volume of carbon dioxide, if we were at STP, would be produced if only 2.5 grams of the CH4 was burned. So we're only going to do 2.5 grams this time. Well, I'm going to go grams of A to moles of A, moles of A to moles of B, but I don't want grams of B. I want volume. So I'm going to have to get from moles to liters. Molar mass, mole ratio, ideal gas law, or you can notice it tells you you're at STP. So if it tells you you're at STP, you're allowed to use that molar volume. Grams to moles, moles of A to moles of B. Now, just for the sake of practicing the newer aspect, I'm not going to use molar volume. I'm going to switch to ideal gas law. You should get the same answer. It'll just be rounded a little bit differently. So I'm going to take this number of moles and I'm going to plug it into the ideal gas law. We have our pressure, we have our moles, and we have our temperature. If you don't feel like using kilopascals and you wanted to use a different unit of pressure, like atmospheres, that's fine. You just need to make sure you use the different R value. So use whatever R value matches your pressures. So go ahead and pause, plug everything into the equation, and try to find that volume of carbon dioxide. All right, when you plug everything in, you punch your calculator, you end up with 3 liters of carbon dioxide. So just showing you a variety of ways these problems can look. Okay, let's do another one. We'll do one more. Ammonia gas can be synthesized from nitrogen gas and hydrogen gas. What volume of ammonia at 450 kilopascals and 80 Celsius can be obtained from the complete reaction of 7,500 grams of hydrogen? First, we need a balanced equation. Remember, hydrogen is and nitrogen are diatomic. Don't forget that. It tells me that I start with grams of hydrogen, so I'm going to go grams of A to moles of A, moles of A to moles of B, moles of B to liters of B. It doesn't want grams, it doesn't want moles, it wants a volume. So grams to moles uses molar mass. Moles to moles is going to use mole ratio. I am not at STP, so I can't use molar volume. I have to stop here. I have to get moles of ammonia. Now I'm back to an ideal gas law. I have all of my values. I plug them in, I punch my calculator, and I get a whole bunch of ammonia. A lot of liters, 16,135 liters. Okay. All right, this is going to be the last one. Hydrogen gas and sodium hydroxide is produced when sodium metal is added to water. What mass of sodium is needed to produce 20 liters of hydrogen gas at STP? So first we need a balanced equation. This time I'm starting with liters, aren't I? So I'm kind of going backwards from what we did on the earlier problem. I'm going from liters to moles of A to moles of B to grams of B. So you pause the video and you try to do this one from start to finish. See what you get. All right, so I'm going to start with an ideal gas calculation this time. I'm going to get from liters of A to moles of A. Then I'm going to go from moles of A to moles of B, moles of B to grams of B. Punch that all in my calculator and I get about 41 grams. So in order to produce 20 liters of hydrogen gas at that pressure and that temperature, you would have to start with 41.1 grams of sodium. All right, so at the end of this PowerPoint, there are a couple extra practice problems, okay? So what I've done is I've given you some extra practice and I've shown you what the pathways are. And I labeled my pathways to show you what you're going to use at each place, okay? So there's 5 of these. I'm not going to go through all of them, but that gives you the idea of what to do if you get stuck. And then at the very, very end are the actual answers, okay? So what I'm going to do is basically click through these one at a time. You will be able to pause the video and do them at your speed, okay? And then at the very end of the video, I'll show you what the answers are. I'm not going to narrate them and walk you through the whole thing. They're just kind of some extras. So I'll just kind of click through and show them to you. All right, so here's number 1. Pause the video and try to get your pathway. Here's your pathway. Now pause the video and try to solve the problem. All right, next question. Pause the video and try to get your pathway. All right, here's your pathway. You can pause the video and try to solve the problem now. All right, here's question 3. Pause the video and try to get your pathway. All right, here's your pathway. Pause the video and try to solve the problem. Here's question 4. Pause the video and try to get your pathway. Alright, here's the pathway. Pause the video and try to solve the problem. Here's 5A. Pause the video, try to get your pathway. Here's your pathway. You'll have to do it 4 times. Pause the video and try to solve all 4 parts of this question. Here's 5B. Pause the video and try to get your pathway. You'll notice this time it's a little bit trickier because what you're solving for is the total moles of gas. So you do add up all your values to get to 29. So your mole ratio is 29 over 4. So just a little bit tricky there. So be a little bit careful. Pause the video and try to solve this problem. When you're done, I'm just going to click through the answer slides for all 5 questions. So pause it and write down and correct whatever you need to. And that'll be the end of the video. Alright, here are the answers. Alright, that's it for this video. I hope that was helpful. Bye everybody.